Okay, this is a volumetric analysis problem where we're looking at the volume of one reactant used for the other one. Something that sometimes happens with these is people see the two volumes and the one concentration, and they think that they're going to use the equation M1V1 equals M2V2, and that's not correct, even though it seems to fit in that. This equation is for dilution. It's not for chemical reactions, so don't use that. If we're going to use this, we need to first get the balanced chemical equation. So this is a neutralization, which is a type of double replacement reaction. I'm going to write my salt first. The potassium with a +1 charge goes with phosphate, which has a -3 charge, so I need this to be K3PO4. And then my other product, hydrogen, goes with hydroxide, is water, so a double replacement reaction. And then let's balance this as well. So I've got 3 potassiums, I'll put 3 potassiums. I'm going to balance this as hydrogen and hydroxide separately. So 3 hydroxides, only 1 hydroxide, 3 hydrogens, 3 hydrogens. And it looks like it's balanced. And then I'm going to put the information that I know here. The phosphoric acid, I have 15.12 milliliters of 0.50 molar. And I'm using that to neutralize 10 milliliters of potassium hydroxide. And I don't know the molarity of that. Okay, so just thinking ahead about what we know about molarity, if I want to know molarity, molarity is equal to moles over liters. And we already know the liters. The liters are, from the milliliters, I know it's 10 milliliters, so that would be 0.010 liters. And so that's already given. I've got one more sig fig there, don't I? Okay, so then we just need to find this. If we can find the number of moles, then we can plug into this and get molarity. Okay, so let's just make a note. All we really need is moles of this and we can get there. Well, we have a lot of information about this reactant, and probably we'll be able to convert back and get the amount of the other reactant. So let's just start with what we know about the phosphoric acid. If I were going to start a conversion factor problem with that information and work into a stoichiometry problem, what should I start with in this first spot? Well, I would start with the one that's 1 number, 1 unit. Remember, molarity is actually moles per liter, so it won't be something you start with first. Typically, it's going to be used in later steps. So I'm going to start with my 15.12 milliliters of phosphoric acid. Okay, and what should I convert to next? I know I don't want milliliters, but I see that if I could get to liters, then I could use this molarity. So let's do that first. And we're still talking about the phosphoric acid solution, so let's put that in there. Okay, and so my milliliters is gone. I have liters of phosphoric acid here. I'm writing phosphoric acid because the H3PO4 because we have 2 solutions in this problem and we need to make sure we keep them separate. So I said that I would go to liters so I can use this molarity. Let's do that now. So this is a molarity step. And the molarity is 0.5, and the 0.5 goes with the moles, 0.5 moles per liter. Okay, and we do that a lot in chemistry. We convert to moles first, we got it to moles, and then once we get to moles, we can switch the units. Switch the substances that we're talking about. So in other words, I can go from moles H3PO4, this is the stoichiometry part. I can go to moles of the substance that I'm interested in, potassium hydroxide. Where do I get the numbers to do this? This is where I use the coefficients. So for the phosphoric acid, it's a 1, and for the potassium hydroxide, it's a 3. And then if I multiply this out and divide, I get 0. Okay, but I'm not there because the problem didn't ask for moles of potassium hydroxide. It asked for the molarity of the solution. So remember back here we talked about doing this? Now I'm ready. The molarity is equal to, now I know the moles, and I already knew the volume. So I get, let's see, 2.27 molar potassium hydroxide.